Lagrangian mechanics. That's what we're doing. We're doing Lagrangian mechanics, and this is one of my favorite problems. So I'm working through a bunch of these problems. If you want an introduction to the Lagrangian mechanics, I have that in my link down below. There's a playlist for the whole classical mechanics course, and you can look at the other ones I've done before too. And I'm probably going to make a mistake, and that's just how these things happen. Okay, so when you're working on the board, you make mistakes. I'll try to fix it. I'm not going to get to the end without a mistake, but I may get, 30 seconds, 45 seconds, 46 seconds ahead before I figure out my mistake, but I usually figure it out. Okay, so this is a problem. Oh, I actually brought a prop. Let me see if I can reach it. So this is the problem that we're doing today. So I made this little fake pendulum. This is a pendulum, right? So it's Lego. I don't know if you know that, Lego. So swinging back and forth like that, that's cool. But this is different. This is what I call the jiggle pendulum. So now, instead of just being a normal pendulum, and we can assume this is massless right here, we only have mass down here. So instead of just being a normal pendulum like that, this pivot point up here is going to be oscillating up and down. Like that. Jiggling. See? It's called jiggle pendulum. And there's something really cool in the end I'm going to show you that I won't be able to really do in real life, but I'll try. So that's what we want to model. We want to model the jiggle pendulum like this. Let's get to it. Okay, jiggle pendulum. So in this case, what I did was I have my mass on a rod of length r, and then the pivot point up here is oscillating up and down with an with a motion of a sine omega t. And I like to use sine because sine starts at 0 at t equals 0, so that's just useful. And we're going to use Lagrangian mechanics. So Lagrangian mechanics, we define the Lagrangian as the potential, the kinetic energy minus the potential, and then we can apply the Euler-Lagrange equation right here to find the equation of motion. Now, the first thing that we always do in a Lagrangian problem is to determine the number of degrees of freedom, determine how many variables we need to represent the system. So for a pendulum, you need one. But what about for a jiggle pendulum, right? And so you might think, well, I need to know the angular position of this, but that depends on where this is too, so I need to know where that is too. So there's two, but there's just one, right? And that's what makes this an interesting problem. Because I have a driven system up here, that depends on time. So if I know the time and the angle, then I know everything, right? So time is moving forward. I don't have to solve for time. So in fact, this is still a 1 degree freedom of one degree of freedom problem. We only need one coordinate. And I think that seems counterintuitive in this case, but it's true. We're going to go ahead and I'm going to go ahead and give you a spoiler alert. There's another really interesting thing here in that energy is not going to be conserved. We talk about Lagrangian, we talk about kinetic and potential energy, and we say, oh, you can't do it if you lose energy, but if you gain energy or lose energy from some driving force, it still works. Okay, we just can't do dissipative forces. Let's just jump to it. Okay, so we want to write down the Lagrangian. Just like with the pendulum, in order to write down the Lagrangian, we have to write down the kinetic energy. And we're going to write down the kinetic energy in terms of Cartesian coordinates because that's what we know, right? I can't just write down the kinetic energy of this as it is. I don't know how to do that. But if I can write it in Cartesian coordinates, if I can get a relationship between Cartesian coordinates and my variables, I'm going to be good to go. So, and the same thing for potential. So I need to get my x and y values for this as a function of time. Okay, so the x value is pretty easy because if this is my pivot point moving up and down, and just so you know, we can have all sorts of jiggle pendulums. You can do this, you could do this, you could do that. Okay, and they're all pretty cool, but I'm just doing a vertical one today. So my x coordinate right here is not too difficult to say. I can say x is going to be r times sine of theta, right? Because if this is my origin, which it is, then r sine theta is this distance and that's x. Pretty easy. My y value, let's say that's y equals 0, so this is going to be negative r sine theta. But the pivot point moves up and down, so y is actually going to be a sine omega t minus r cosine theta. That make sense? So just like with the pendulum, we didn't have this. And in fact, we're always going to think about what happens if A goes to 0. The amplitude of oscillation goes to 0. You should get back to your pendulum because it's a normal pendulum then. Okay, and we'll check that later. Now that I have x and y, I can take the derivatives and then square them and put them in there. Yes, it's going to get a little bit messy, but not too bad. So let's put it up here. I'm going to take the derivative of x. X dot is going to be equal to, r is constant, but theta is not. Theta changes with time. So I have to take the derivative of sine theta, which is cosine theta, and then I have to take the derivative of theta. So I get r theta dot cosine theta. Now I need to take the derivative of y dot. Now here I have time and theta both change with time. So I have to take the derivative of this with respect to time. So the derivative of sine omega t is going to be a omega cosine omega t, right? So I took the derivative of sine omega t, and then I'm going to take the derivative of the inside, which is omega. And then I have to take the derivative of this, so it's going to be plus r theta dot sine theta. Did I run out of room? I made it. Okay. I always get worried about this side of the board. I don't know why. I'm really a this side of the board kind of person. We're going to need to square those. I'm going to go ahead and square those. I'm going to erase. This is going to come back. This is like super important. So I want to put it over here, a little bit over. X equals r sine theta. Y equals a sine omega t minus r cosine theta. Let's put a box and protect that because we are going to need that at some point. We can remember the Lagrangian, so we got plenty of room now. So I'm going to write this as x dot squared. That one's pretty easy. It's just r squared theta dot squared. That's a theta. Theta dot squared cosine squared theta. Now y dot squared, we have two terms. Okay, so let's just do it. So this is going to be equal to a squared omega squared cosine squared omega t. That's that first term squared. And then I'm going to get the cross term, so I get two of those. So I get plus 2a omega r theta dot sine theta cosine omega t. I know it's getting messy. And then I have that last term plus r squared theta dot squared sine squared theta. So we can write the kinetic energy term now. So let's go ahead and think, right? Because when I add x dot squared plus y dot squared, I'm going to get this term plus that term. They both have r squared theta dot. See, what did I say? 45 seconds. I said 45-second rule, right? I found my error. So they both have r squared theta dot squared. I can factor that out. I'm going to get cosine squared plus sine squared is 1. So that's good. So let's just write this out. I'm going to multiply out with the 1/2 m and for all of them. So I get 1/2 m r squared theta dot squared. That's these two terms. And then I have this term plus 1/2 m a squared omega squared cosine omega t squared. That's that term. And then this term, the 2 is going to cancel. So I have plus a m, I got a lot of order, omega r theta dot sine theta cosine omega t. And if you may be thinking, there's no way we're going to do Lagrangian here, it's impossible. It's not impossible. It's not even that. It's not going to be that bad. It's not going to be that bad. Okay, so that's t. Let's just go ahead and write down u up here, and then I'll subtract it off up there. I guess I should write it up here. So let's write the whole Lagrangian. I can erase this part. I need a lot of room. Okay, not too high. Okay, L, so it's all this stuff. 1/2 m r squared theta dot squared plus 1/2 m a squared omega squared cosine squared omega t plus a, I'm going to put the m in the front, m a omega squared r theta dot sine theta. I'm writing small so I don't run out of room. Sine theta cosine omega t. And then I have to subtract the potential, and the potential is just mgy. So that's going to be, this is y. So it's going to be minus mg a sine omega t, and then that term, so it's going to be plus mg r cosine theta. So let's just take a moment and check, right? We can do one check, even though it doesn't tell us that we're right, but it will tell us if we're wrong. And that's to say, okay, again, I'm going to apply my a equals 0 condition. So if a equals 0, then I should get a pendulum, right? And we know we've done that one before, so we can just check. So if a equals 0, I get that term goes away, that term goes away, that term goes away. So I have 1/2 m r squared theta dot squared and mgr cosine theta. That looks like the right thing. Okay. So that's good. Okay, now we can apply our Lagrangian. So let's do this in parts. I'm going to first take the partial of L with respect to theta. So let's go through and find all the theta terms. It has to be a theta. Okay. So no theta, there's a theta. So if I take the derivatives, the partial derivative with respect to theta, I'm going to get cosine theta. So that's pretty easy. So I have m a omega squared r theta dot cosine theta cosine omega t. Theta dot doesn't count. That's a partial, right? I'm taking the partial of that. Now I'm looking more, and here's another theta. So I get minus mg r sine theta. See, it's not that bad. Okay. Now let's take the partial of L with respect to theta dot. Okay, we got more terms here. There's one. So I get m r squared theta dot. I'm scanning for theta dots. There's one. Okay, that one's pretty easy, so I just get plus m a omega squared r sine theta cosine omega t. Scanning, that's it. Okay, so now I have to take the derivative with respect to time. So now that does get a little bit messier, but that's fine. The derivative of that with respect to time, the partial of L with respect to theta dot. Okay, so the derivative of this with respect to time, I can do that one because m's constant, r is constant. So I just get m r squared theta double dot. Good, okay. Now this one, let's just think what terms in here depend on time. No, 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 yes, yes. So I only have 2 of those terms depend on it. Let's do this one first. If I take the derivative of sine theta with respect to time, I'm going to get cosine theta theta dot. So let's just write that. Plus m a omega squared. Is that omega squared or theta dot? I think that's just omega. Where did that come from? That came from that term up there. Or there was already a theta dot in there. Already took the derivative of that. Okay. That doesn't like. Me no likey. Because I have theta double dot and then I have omega squared. It's going to be in radians per second squared times. See, I got the wrong units. Okay, look at my cheat sheet. I actually made a cheat sheet because I worked this out beforehand. Let's just see what I did wrong. Because I have 45-second rule, remember? Okay, so L is 1/2. Where'd my 1/2? 1/2. I totally messed up. Because there was another one. Oh, there's that 1/2 omega squared term. Okay, I got that. 1/2 omega squared. That was the omega squared term. So yeah, the MA, that's not squared. So that's not squared. That term came from, yeah, that shouldn't be squared. I don't know why I squared it. I fixed it though. That term squared. Okay. Sorry. I said before, you can't say, oh, unclick, unsubscribe because I made a mistake. I told you I was going to make a mistake. I didn't make it on purpose. Okay. So that's that. Then we're back over here. Okay, I caught it. No, that's the important part. So that's not squared. That one's squared. Okay. Whew. Theta dot. No. So I took the derivative of this with respect to time, and I got the theta dot r cosine theta cosine omega t. And then I have to do it for the cosine omega t, so I'm going to get another omega squared right there. So plus ma omega squared r sine theta sine omega t, and that's actually minus. Check me. Okay, now this stuff has to equal that stuff, right? Because this minus this is 0, so this is equal to that. Number 1, let's just get rid of these masses because there's a mass in every term. Mass, and I can do it with my eraser because it's fine. Okay. Now the next thing I'm going to do is to divide both sides. This is equal to that. But I don't want to rewrite the whole thing, so make a mistake. I'm going to divide both sides by r squared. Okay, so I'm going to divide everything by r squared. So that one's gone. And this is a, I'm going to write this as a over r. I'm going to write this as a over r. I'm going to write this as just r. G over r. Yeah, that's right. And then this is going to be a over r. Now I have theta double dot. That's what I want. I want theta double dot. So theta double dot, I want to get it by itself. So I'm just going to subtract this from both sides, add that to both sides, and we can write down the whole thing. And I don't even want to do this, but let's do it anyway. So theta double dot is going to be all that stuff. A over r omega squared theta dot cosine theta cosine omega t minus g over r sine theta, and then I have to subtract that, minus a over r omega theta dot cosine theta cosine omega t, and then plus that, plus a over r omega squared sine theta sine omega t. I know it's messy. I know it is, but let's see. Right here, this, oh, there should be an away. So, aha. Okay. So, but look what happens. That and that cancel. They're equal and opposite. So I just get a over r omega, no, I don't get that one. Negative g over r sine theta, and then this other term over here. Okay, and let's check. Remember, if a goes to 0, that term goes to 0 too. So that's pretty good. Let me double check right here what I had. Let's see. Wait, did they cancel? This is a hard problem. I mean, it's not hard, messy. Cosine omega theta, cosine omega t, yeah, they cancel. Okay, so I'm pretty sure that's fine. So now what do? I mean, I don't want to solve that differential equation, so I'm not going to. I hope you wrote that down. So I can use delta t 0.01 seconds. You know what's coming next. And if I assume that time interval, I can calculate theta double dot and assume it's constant, so that theta double dot is equal to delta theta dot delta t, which is theta 2 dot minus theta 1 dot over delta t. So this gives me theta 2 dot theta 1 dot plus theta double dot delta t. So this is the angular velocity at the beginning of the time interval. This is at the end. So if I know the beginning, I can calculate the angular acceleration, multiply by delta t, add those together, and that's my new theta dot. And then I can do the same thing for theta dot as delta theta over delta t, and this gives me theta 2, theta 1, plus theta dot delta t. And then I just do it for again and again and again and again and again. Okay, so I'm still not convinced that my solution's not correct. There might be an error, but I'm going to plow forward, right? Because what am I going to do? Start over? It's been 20 minutes right now. I'm not starting over. Okay, so let's do this in Python. And we're going to actually make a visual animation. So I'm not just going to make a graph. I'm going to animate it in 3D because I think that'll be cool. Okay, jumping in to the computer. Web v Python. Okay. Let's go ahead and get our constants in here. G is 9.8. R is 1. I just pick a 1 meter thing. A is 0.05. I don't know, 5. Yeah, let's just try something small. We can change that. Omega is going to be equal to, let's say, 5. I'm just picking something. T equals 0. dt equals 0.01. Okay, I'm going to make 3 objects. I'm going to make a top oscillating mass, and then I'm going to make my hanging mass, and then I'm going to make my stick. So let's just call that top a mass. It's a sphere. It has a position of, let's just put it at the origin, and the radius is going to be equal to 0.01. I don't know. Let's just make it like that. And let's just go ahead and animate the top. I want it to oscillate up and down. So I would just say while t is less than 4 for 4 seconds, rate 100, so I'll only do 100 calculations per second. Is that big enough? Maybe that's bigger. I like it big. So now I'm just going to, let's just move it, right? Top.pos equals vector 0, a times sine of omega times t, 0, and then I'm going to update time. Let's get something working here. Always start building things in parts. Okay, so it looks weird because the camera zoomed out to make everything fit beforehand, but it seems to be working. Okay, now let's make, I need an initial angle. So theta equals 22 times pi over 180. I'm going to need initial angular velocity. Theta dot equals 0. Okay, we'll need those. Let's make our mass. Mass is going to be equal to a sphere. Position is going to be equal to, so since my top is initially at the vector 0, 0, 0, it doesn't really matter, but let's just go ahead and type in our normal equation for x, y, and z. So it's going to have a vector. The position is going to be equal to vector r times cosine theta, right? That's exactly what I had up there. Y is going to be a times sine omega times t minus r times sine of theta, and then the z coordinate 0. Now I need to give it a radius. It should be bigger, so radius is 0.05. Color is yellow. And then make trail equals true. Make trail equals true. Okay, let's just run it and see if it's even there. Okay, it's not even animated. Okay, so there's my mass. That doesn't look right. (22 theta). It's so far off. Position vector r. Oh, that's right. This is sine, and that's cosine. So there's that looks good. Okay, now let's put our stick, and I'm going to call it a stick, because why not? Doesn't really matter. Stick is equal to a cylinder. Position is going to be top.pos, and then the axis is going to be mass.pos minus top.pos, and then the radius is going to be equal to, let's see, how big is that sphere? 0.02, and let's put this at 0.5. Let's see what that looks like. Okay, and so that top mass is oscillating up and down without any connection, because we haven't done any of the calculations yet. Let's make that top a little bit smaller, just a tad bit smaller, 3, maybe it's something like that. Okay, good. We're all set. So in this loop, what I need to do, I can do that. I need to go ahead and do my calculations. So I'm going to calculate theta double dot. Theta d dot is what I call that. And I just need to type my equation right here, which is negative g over r times sine of theta. And then I have plus a over r times omega squared times sine of theta times sine omega t. Oh, no, aha, times. Okay, so now once I have my theta double dot, I can update theta dot. Theta dot equals theta dot plus theta double dot times dt. Now I can update theta. Theta equals theta plus theta dot. Nope, theta dot times dt. Now I can move my stuff, right? So I need to move my mass. So the position of the mass. If you want, I could just say x equals r times sine theta. Y equals a times sine omega times t minus r times cosine theta. And then mass.pos equals vector x, y, 0. That's fine. Now I need to move my stick. So the cylinder has a position, which is where it's going to start, and then the axis from the start to the end. So the start's at the top. So stick.pos is top.pos. And then stick.axis is equal to mass.pos minus stick. No, top.pos. If that works, I'm going to be very, very surprised. I mean, it looks like it's working to me. It's kind of fun to just look at it, huh? Okay, let's just double check. Let's just double check by putting a as 0. I said that we should do that. I mean, it definitely looks like a pendulum. So I'm happy with that. Okay. And now there's a whole bunch of stuff you could play with right here. But let's do this. Let's increase that frequency super high. So I'm going to actually put this at 1,000, and this at 1,000. And let's put this at 200. Let's just see what happens there. Oh, I'm sorry. Forgot. Okay, so that looks a little jerky. I think I don't have my time step small enough. So let's just put this down to 100. It still looks a little jerky, but I think it might be okay. Okay, now the awesome thing, it turns out that if you invert this and you have a very high frequency, it's stable. Let's just see if we can make that work. So I'm going to start my starting angle at something close to, vertical will be 180, so let's do 175, and let's just run it. Isn't that cool? This one's not completely stable, but this is a real thing, and you can make this. You can make a jiggle point with a stiff rod at the top, and you can shake it, and it doesn't fall over. So that works seems to imply that the rest of my code is right. I may have made an error and still just magically it works, but if that's the case, I'm sure you will let me know, because you guys are great at finding my errors. And I do, like I said, I do make errors, and that's the point, right? That's a lot of algebra, and it's hard to keep up with stuff. And if you make a mistake, you need to go back through it, but just keep working at it. And it's the big idea that's important. I will show you a way to do the algebra with Python. I'm not going to do that today, but there is a way to actually algebraically solve for those things for complicated situations to make sure you're right. And I will show you that, but If you made it this far, that link to this code is down below. The playlist for the whole thing is down below, and that's that. We're going to do some more Lagrangian problems. Oh, I should give you some homework. Plot the energy as a function of time. Is energy conserved? It's not. Okay. So it can be kind of conserved in some of these cases, but you can get cases where it's not too. So that's that. Talk to you guys later at the end. Had fun with that.